Hi friends, do you remember the 90s? More specifically, the mid to late 90s. It was a strange time when, by law, every game company had to produce a colourful mascot platformer. And this is one of them. This is Adventures of Lomax from 1996, and it was a platform game spin-off of Lemmings. It was released for PlayStation and for Windows 95, and it features this incredible pixel art from Henk Nyborg, who was a gentleman who started out on the Amiga and went on to work on a number of impressive titles like Shantae and the Pirate's Curse and, more recently, Shakedown Hawaii. Anyway, I wanted to put together a video explaining how to reverse engineer a game from scratch. So I was rifling through my collection and found this. My copy was the Windows 95 version, but the good news is the data files are exactly the same for Windows and PlayStation. In fact, the footage you're watching right now is from the PlayStation edition because the Windows edition uses a very old version of DirectX, and I could not get it to work without a ton of visual glitches. But enough talk, let's reverse a thing. Right, I have my Windows copy of Lomax here, and the plan for today is to just try and have a look inside some of the files. So the very first thing that I'm going to do is run a histogram on some of these files. I'll be using this tool MRC Hist, which is part of Mr. Crowbar, the Python framework that I'll be using for most of the rest of this video. A histogram is very useful for figuring out what type of data is inside a file that you know nothing about. It basically visually shows how often each byte from 0 to 255 appears in a file. Let me just quickly run one now on the exe file for this game. Lomax exe. There we are. So for the output here, each line is actually a separate histogram containing a single slice of the file. So the left column here is just the start offset of each slice. The middle is a heat map ranging from 0 to 255. It's kind of been compressed a little bit to fit on the screen, but 0 is here and 255 is up here. And the end is a value that's known as the Shannon entropy. The Shannon entropy is, it's just a number between 0 and 8, and the easiest way to think about it is a value of how compressed the data currently is. Generally speaking, 0 to 7.5 is uncompressed data, 7.5 and higher is compressed in some way, and like the really high ones like 7.999, that's pretty close to random noise, and so there's probably going to be some kind of strong encryption like AES. A good rule of thumb, if the data is actually compressed, you can't really do anything with the file until you learn how to decompress it first, so it's best to focus your efforts on taking the program apart and figuring out how the compression works first. So at first glance in a hex editor, an exe file looks kind of random and indecipherable, but the histogram shows that there's quite a strong pattern in how often certain bytes show up. For instance, you can see the very strong vertical lines, and these would be x86 instructions that are extremely common. Also, you can see around here that the entropy for the most part is around 6, so there's definitely no compression. Actually, if I scroll down all the way down to here, you might see these bands around here, which are very strong in the second quarter of the range, and that would be because they are plain text, because as it turns out, all the letters of the ASCII alphabet are in this little range here. And yeah, it kind of comes down to personal preference, but I find it quite nice to have this sort of visual fingerprint, because you can tell from a glance that like a file with this sort of stringy looking pattern in the histogram, it's probably going to be a program, because most programs kind of look the same. Anyway, that's by the by. I think all the graphics for this game will be stored in the Worlds folder, so let's have a look. Yep, Worlds. Alright. Let's try going for... Let's have a look at main.world. That seems fairly important. Just reducing the number of samples because I know that these files are quite small. By default, it's kind of set up for slices that are about 16 times as big. Interesting. This is actually really encouraging, I've got to say. But look how low that entropy is. It's barely compressed at all. And Yeah, it's got this kind of banding going on. Let's try opening another file. See how it looks. Go for the title screen because I imagine that there'd definitely be graphics in the title.world one. Yeah. Interesting. Okay. This looks like raw graphics. Just the kind of the distribution of it. Just something about the fact that it's in these little small bands here, and I kind of know from looking at the game that it's definitely going to have kind of palette-driven graphics, and not only that, the palettes are going to kind of be ramps from kind of dark to, usually the way that the palettes in these games are organized is that they've got like little ramps going from like a dark color to a lighter color, which would mean that if they use a whole bunch of the same color in the same spot, there would appear as a little blob here in the histogram. I reckon, you know what? I reckon we can figure out how these files work just by looking at them. We don't even have to take the program apart to figure out what's going on. Like, with entropy this low, there shouldn't be that much in the way of complicated stuff. Yeah, at first glance, it looks like they've kind of got a bit of a header area at the top, maybe. Some definite sort of... There's definitely some kind of complex information at the very start, but then the rest is just simple as, so that's got to be just raw graphics down there. Yeah, let's try that. Let's just try taking the file apart. Right, so I'm just going to begin by creating a work file for today. Just a normal Python file, nothing too serious. This is going to contain all of the classes that we use to model the data that is in these files. So I'll just start off by importing Mr. Crowbar. Yep, so that should get us started. And then I've already added the virtual env to my current shell, so I am just going to open up IPython. You haven't used IPython before, it's very similar to the normal Python shell, except that you've got a whole bunch of nice things like print options, command history. Entering in multi-line is much nicer than the default. I'm going to stick with the title screen for now, so let's just open up world's title.world, read it in as bytes. There we go, 353k roughly. I'm just going to import my helper library here. Let's have a look at the beginning of the file. For this, I'm going to use... So I'm just going to quickly use my hexdump tool here. The method utils.hexdump, it's very similar to the command line equivalent that I include with the software package mrcdump. You can provide it a source containing all of the bytes. You can then pick which section of the file that you want to see with start, end, and length. And then you can change the grouping with major len and minor len, which in this case, I don't think we'll have to do that. So we're just going to do a normal dump of the first 200 bytes of the file. Cool. First impressions looking at this, it seems to have a file format that's kind of similar to what you'd see in Riff, which is basically it is a stream. Each bit of the file just appears like in sequence without a big index at the beginning. Each chunk of the file is prefixed with a magic number, which is usually human readable. This is quite similar to how it appears in Riff. Riff gives you 4 bytes for the ID, and usually that's large enough to put in a text hint as to what the chunk of the file is going to be about, but also 4 bytes is quite nice because it fits into a single 32-bit int, which means you can deal with it as a number. And usually after the ID, you would have a size, which is also an int. And that number is just how many bytes the following data section is. So if we were to read this, we'd say that the ID for the first chunk is world, the size is 8 bytes, and then it is followed by this data here, which is inside the chunk. It's slightly confusing because it looks like it's going to be... It almost looks like it's actually just continuing on like that, but I'm just going to assume that this is something special. And in fact, the next chunk is this NMY. one here. So a good test to see if this is accurate would be to take, so we've got the ID here, NMY. We have this size afterwards, which is OA2C. And then the data begins here at offset 18. So in theory, if we add together offset 18, which is the start of this data section here, with A2C, which is meant to be the size of the data, the address that we get at the end will be where the next block starts, which should be an ID. A44, okay. So let's do another dump, this time from start, from A00 to C00. And what do you know? It's another ID. I think that we're onto a winner here. The good news for a field like this is that it's so common that Mr. Crowbar already has built-in support for the type of structure that we have in mind. So to that end, I am going to start writing my data model here. Now in Mr. Crowbar, data model is known as a block, which is to say a single collection of bytes, which can contain either fields such as numbers or strings, or other blocks arranged in certain ways. So this particular arrangement I have written in Mr. Crowbar, I have decided to call a chunk stream. To begin with, let's just create a block. Block is just a Python class. We'll call it world because it's going to be the block that deals with the entire file. And inside the block is going to be our, let's just call it chunks. And that is going to be of type chunk field. Now, usually the way you set up a chunk field, it's so that you can map each of these IDs here back to a type of block that you want to interpret it as. Right now we're just exploring, so it's not that important. We're going to, the very first argument to chunk field is a mapping between ID and block class. We don't have any of those yet, so we're just going to leave it blank. So we're going to go, so I'm going to create a field here called block map, which is empty. The second argument is going to be the offset to the start of the file, so that is going to be 0. And once again, I am drawing a blank as to how to use my own library, so I am going to check the doc string. Yes, so obviously if you have a nice IDE with auto-completion, you probably won't need to kind of go back and do this. This is just how I've gotten used to doing it. Yeah, you can see there. So argument 1 is the chunk map, argument 2 is the offset. Now for defining this, I think the only thing that we need to be clear about would be these ID parameters here. So ID size is quite important, and length field is also quite important because that is that number of bytes thing that follows the ID that I mentioned earlier. So I'm going to say the ID size is 4 because it's 4 bytes. You can make this an integer if you want, but by default it's bytes, which again, nice and easy to read. And length field, and this just takes a normal Mr. Crowbar type. So I think for this case, looking back at this, yeah, okay, so it is a it's an unsigned big endian 32-bit integer. So one important thing that I forgot to mention, when working with a chunk field, it's always important to mention a default class. So by default, this block mapping here, if there isn't a correct map between the ID of the chunk that you're trying to load and a class, it'll throw an exception for not being able to find it. If you set default class here, then any of the non-matches will be attempted to be loaded with that type of block. So in here, I'm going to make the default class MRC unknown, which is, it's a built-in block and it's pretty simple. There's just one field in it called data, which contains the raw bytes. So it's very useful for prototyping cases like this. Okay, we have our data model, we have our file. I think it's time to give it a try. And there it is, it's world at the top. So to load the file with the model, we just do this. And there we go, we've got our object. The field that we made in our model is chunks, so let's have a look at AX chunks. And here we go, we have all of the chunks that are there in the file, stored as unknown objects. Interesting kind of spread of IDs. We've got world, NMY, I guess that means enemy. Para, that, if I recall, that was text, so I'm guessing it means paragraph. All sorts of stuff. But hang on a second, all the way down the bottom we have all these anims here. These look very promising indeed. Alright, let's pick one of these anim objects and see what's inside. Yeah, that'll do. So the object is of course this unknown, which contains a single field, data, which contains all the stuff as bytes. How long is it? Fairly big. How does it look in a hex editor, I wonder? Already, this looks extremely picture-y. Like you can see there's lots of kind of recurring patterns. There's this kind of weird sort of interlacing artifact which indicates that the stride of the hex editor screen isn't quite the same as the stride of the picture, but oh, and there's like a little bit of header information at the top. So that was a hex dump view. Let's try a graphical view. Oh, yeah. Interestingly, like there's definitely something image. Well, this is very clearly a picture of some description. It looks like there's actually multiple frames, perhaps, and each of the frames is a slightly different size, because you can kind of tell by the interlacing artifacts here that there are kind of there's definitely like a different width going on for each of these sections. Let's see if we can get one of them into sharp focus. So there is actually a kind of a useful tool in Mr. Crowbar for doing exactly this. It is a variant of pixdump. There it is, pixdump sweep. So the arguments are pretty much the same as pixdump, except this time you get the chance to provide a range of different widths to render as, and that way you can kind of work backwards and figure out what width the image data is actually at. It's probably still going to look a little bit off because we've got the header that's kind of pushing everything out to the side, but it should at least look in focus and not interlaced. So for now, I'm just going to save this to a convenient letter. Now we'll take our pixdump command. Let's go range from, oh, I don't know. Let's go from 16 to 32. Let's call it half a second delay. There we go. So we've got one graphic that's in tight focus around here. It looks like a fish. I think it might be the snappy fish underneath the bridge at the start of the game. There we go. As you can see, when you slightly change the width, the graphics themselves sort of move in and out of focus for each step. So you can see like the very first frame, that's going to be about 28 pixels wide, or at least that's what's expecting in order to get the nice in focus width. Also noting this, we're not dealing with the color information yet. This is just a test palette which goes from extremely dark brown to light yellow, which I found was quite helpful for picking out graphical information. Chances are the palette is going to be stored somewhere else in the data that we will find later on. But for now, let's start with this first frame here. So this first frame here is definitely 28 pixels wide. We've got some information in the header up here, followed by what looks like 4 frames of animation. So we should be able to look at that header and come to an understanding of what's going on. Let's have a look at that hex dump of the start of it again. So off the bat, I don't really know what much of this stuff in the header does. I think it's probably safe to say that this here is probably going to be the number of frames, because it's 4. And in fact, I imagine it's going to be split up into 2 sections. There's going to be one section which is relevant to the entire chunk, and there'll be one which is at the beginning of each frame, which contains the width and the height. So say that we count everything from here on as being part of the per frame information. $56. Okay. That's quite interesting because the picture information that we got from looking at it was about 28, which that'd be half. So, and now that I think about it, if we have another quick look at this. Yeah, this does kind of look a little compressed in the width. Like the height looks okay, but width-wise, it kind of looks like it's kind of stuffed in there into the width. Maybe there's something going on with the width, and it is in fact 56 pixels wide, but it's just stored in a strange way. Yeah, okay. I might see a pattern here. So for these lines of pixels, I can't help but noticing that quite a lot of the lines begin with a number that has a 0 in the second digit and a 0 in the first digit at the end, which could in fact mean that maybe these sprites are 16 color and each pixel is in fact just 1/2 of a byte. So this is 1 pixel, this is 1 pixel, this is 1 pixel, and so forth, and stored in, I guess, little endian order, which would mean this is the first pixel, this is the second pixel, this is the third, this is the fourth, etc. And that would take into account the fact that the width is half. Interesting. I guess maybe we'll have to do some weird unpacking. But that all adds up. So that would mean that this value here is the width, this is the height, and these are something else. But then after that is the image information. Doesn't look like there's a file size, so I'm guessing they figure out how big the data is based on width times height, which, yeah, makes sense. We can do that. So let's have a go at trying to model some of these findings that we've made. So there are all these other things in the header that we don't quite know what they are, and that's okay. At this stage, all we really need is enough to just take the data apart and reassemble it in a way that makes sense, aka get the images out of here. And I think we've got enough to go on for that. We've got a number of frames, and we've got a width, and we've got a height. So let's try and model what we found out. So I think I'll start off by making another class for the anim. And in this class, we know it's going to begin with 2 things. We don't really know what they are, so we'll just put some placeholders in. And then the next one will be the number of frames. And then after that, and following the number of frames, we don't really know what that is. That kind of looks like 2 separate bytes. So we'll put in a couple of placeholders for them. 6 and 7. And then after that, yeah, that looks like one big integer. So we'll put another placeholder in for that. And now after this, we're going to have per frame information. And I think for this, we're going to model that in a separate block to what we've got for our header information so that we can then repeat it. So, yep, so we've got our width and our height, and then 2 unknowns. And then after that is the raw data. So we'll go data, or raw data, bytes. And the default for bytes is basically, if you don't specify a size, just return all of the information that is provided after that. Oh, and I made a mistake here. That should be height. And now for size. Now we were saying before that it doesn't look like there's a size value, so we're going to have to calculate one. Luckily, we can do that. We will just generate a property. And we're going to call it size. Then in here, we can go length equals a reference to the size. And that way the loader, initially it'll start off by trying to load the width and height fields. And then when it reaches this and it tries to evaluate how long it needs to load in, it will do this calculation here, which will read from width and height. Now going back down here, we obviously want to load in our frames, so we'll go frames. And this time we're just going to load in a block field. So unlike the previous time we were doing a stream-based field, there's no ID or size. It's literally, I think the instruction is just going to be keep loading in frames until you run out of data. So the class we're going to use is our frame class that we just made. The offset is going to be at 0C, I think. That's 8 plus 4 in hexadecimal. Stream, yes. It's going to be one of those. And I think that might be enough. One other thing. It would be quite nice if we could just embed some kind of quick shortcut way of doing this pixel representation here so we don't have to like type in all of the commands to pick stuff and stuff. And would you believe it, there is a nice and easy way of doing this in Mr. Crowbar as well. It is known as a view, and we actually have a nice one for displaying information. To use it, we actually have to import another library up here. I believe it is the images library, so from Crowbar lib images import base as image. And then here in the constructor for anim frame, so we're just going to make a quick pass through here to go to the default constructor. And then under that, we're going to add what's known as a view. So we'll call our view self.image. And this is part of the image library. It's known as indexed image because it's referring to a paletted image underneath. I'm slightly cheating. The documentation is on the other screen here. So the first argument is self. Views take the class, well, the block class of the first argument. Then there'd be the width and the height, which are properties or references to the width and the height that we found. Then there's the source, which of course would be our raw data. And then palette. We don't really have a palette yet, so I think we'll just leave it and it should fall through to the test palette, much like PixDump does. And that should be enough for us to have a look at the image data. So we'll save that. Ah, I missed a step. I missed a step. What I forgot to do here was, of course, update this map to load blocks with this anim class here. So let's quickly just do that. And technically I'll just move this down underneath so there's not as much ambiguity. And anim. So there we go. So now every time this chunk field sees a chunk that begins with the ID tag of anim, it'll try and load it this anim block. Let's try it the old-fashioned way. Oh, that's right. I gotta actually open up the file, load it in, and this is a common occurrence. Sometimes I make an error. Okay, so I made another little mistake with the code that I put together. So it turns out that there is a little bit of extra information in this block, and I completely forgot. You don't have to actually turn this into a stream because we know how many frames there are. So we should not be using stream here. We should in fact be using count. And that should be a reference to the number of frames. Also, initially I was just looking through the hex dumps before and it looked like everything might have been rounded off, so I added this alignment equals 4. I'm going to keep it in there for now because there was another bit which looked sort of like that. But basically what this line means is that for each of the frames, just make sure that the amount of data they give is rounded up to the nearest multiple of 4. So let's give this another try. Load in the file, load in the world. That worked. Okay, and then load in our object. Okay, so we've got our anim there. How many frames are there? Just 3 frames. That's not ideal, but we'll keep going. I was expecting 4. And we've got our images. Let's see how this looks. Jump cut. I fixed a bug. To be honest, I thought that I'd overhauled all of the image handling code to have the test palette as the default. Indexed image didn't, so that's now been fixed. So we should have better luck this time. So if we import all of our stuff, load the file, load that, and then load in our example frame. Please work. Yeah, look at that. All right, so, oh, okay. I see what's happened. So technically this is working fine. I just conveniently forgot that the width and the height, the width of the image is doubled in the case of this shark, hence why it appears twice. It's actually just the same image kind of spread over 2 tiers. And it's also including part of the next frame down, which is of course probably freaking out the parser an awful lot. So to get around this, yeah, that's unfortunate. I hope that I wonder if all of the images are encoded like this. No, there's got to be some that aren't, because I know for a fact there are images in this game which have more than 16 colors, if it is indeed the 16 color split thing. So let's try a different picture from our index. 22. There we go. Okay, this looks more like it's the right width. It's quite dark, but I'm assuming that's just because of the color distribution. Like, this looks like this looks like an enemy sprite. It's definitely got an enemy sprite vibe about it. There, look at that. I think we're on the right track here. Now, well, two mysteries left. One, how do we deal with the half-width images? And the other would be, where are all the colors stored? I'm guessing the colors are going to be stored in one of the other sections that we haven't looked at yet. So I had a quick look through the other segments of the file, and unfortunately none of them really kind of immediately jumped out at me as having anything that would kind of look like color information, which is a problem for us, because obviously we want to be able to see how the pictures are meant to look like. We do have a sneaky strategy, though, for trying to figure out what's going on, and that would involve modifying information that we know about. I reckon in order to get the color, or get a lead on how we should find out more about the colors, let's just take one of these images, put in a string of numbers from 0 to 255, and hopefully we should be able to look at that now. I wonder if I can find the title screen image. It will probably be it's got to be one of the first ones in the list, surely. First frame, obviously. Oh, yeah, okay. This looks like the title. Let's try that again, but slightly smaller so it will fit. Yeah, okay. So this is the title screen. Cool. So I reckon I'm going to just start off by creating... It is about 128. It's got to be at least 128 pixels wide, right? Yeah, I've got plenty of room. All right. The beauty of using the model framework like this is that now that we've done our edit, we should in fact be able to export this to another file and run it in the original game. So in order to do that, AX I think was our original world object. Yes, it was. So I'm going to make another file. Let's call it worlds. And I'm just going to export the contents of this object here, which will include our frame with the modified information. Why do these things have to happen when you turn the camera on? And that's another jump cut. So the issue that was happening was related, again, to the 16 color half-width images that we saw before. Basically, the exporter was looking at width and height and assuming they were full width. I put in a bit of a hack here so that... Actually, to go backwards a little bit, I did check out all of the images in the set that were half width and found that they actually had one of the 8 bits in the header, which was set to 1 for each of them. So I've marked this out as, well, imaginatively named 4-bit. And then from inside the animation frame class, I've got this little bodge here for the size method that basically checks to see, is that bit in the header set? And if so, it then divides the size by 2, which then provides the right number of bytes for the output. So I believe now we should be ready to do our change and export it out to a file. I'll just power through that. Oh, the other nice thing, I just added the steps we were doing to the bottom of the work file, which then just saves the job of having to remember all of the things each time. Brilliant. Okay, I've switched out our new title world for the old one, and now we're going to try running it in the game. So I apologize in advance for all of the crazy graphical artifacts that are going to result. As I mentioned before, this is quite an old game. It uses Direct 3D version 2, which I think is not very well emulated inside Wine, hence why anything which looks slightly 3D doesn't work. Also, the transparency is off because when they wrote it, it was designed to only work with 16-bit color, which I'm not going to set because that screws up too many things. Look at that. That's what we're after. So you can see there in the top right corner of the logo, we have all the colors of the palette. I'm going to take a screenshot and we're going to zoom in on that. All things considered, it's quite a nice palette. It's expertly designed. You can tell just from the small number of color bands that they've got here to represent all of these different tones in the scene that whoever designed this clearly went to a lot of effort to make sure that there was that nice color differentiation, those nice little gradients, and yeah, using a small number of colors to full effect, as you can see to some of just the immaculate detail on this logo here. I'm going to be honest, like none of the information that I came across during my travels really seemed to match up with this color information. I might do a manual export of the color, the RGB information from this bitmap and try again just to match up again. But I think there might be some kind of weird encoding, or worse, it might even be in the EXE. I really hope it isn't in the EXE. Okay. So get this, I'd given up for the night. I was just kind of taking a shower just before going to bed, and then something about this picture here just sort of struck me as odd. Or rather, it struck me as odd before, but I just kind of brushed it away, and then just the puzzle pieces just kind of merged into place. And in fact, again, not sure if YouTube is going to show this up. The color reproduction isn't usually the best, but it was these pixels here. These ones here. On my monitor, they look distinctly just slightly greener than the rest of this band. And that, to me, doesn't really make sense, because if you're the pixel artist and you're very deliberately picking these colors, why would you pick ones which are very slightly a different hue than the gradient range that you're going for? And there is actually like a very simple explanation as to why, and that would be you're not using RGB, you're using a different color space. And mentioning before that this game is designed to work in 8 or 16-bit color mode. 16-bit color mode, that is usually 5 bits for red, 5 bits for blue, and 6 bits for green, because the eye is said to perceive green more, so they give green a little bit more. But because of that, that means that certain shades are slightly greener, so maybe these colors are stored as 16-bit somewhere in the file. I didn't even think about looking at 16-bit because generally they don't quite show up. Or worse, maybe they're stored as some other kind of format, and then Direct 3D or Direct Draw is translating them back into RGB through some God knows how transformation, which means they won't appear as these RGB numbers in the file or appear as something else. And I think I'm on the right track there. I think it's going to be 16-bit. It's going to be some kind of 16-bit. Right, so I had another look at this head chunk over here, and I noticed something quite promising. It's not immediately obvious when you look at it, but if you check out this section of data here, have a look at this column of numbers here. None of them go above 7F. In fact, this column here goes from about, goes from 0 to FF, but the second column, it always is underneath 7F, which means that if you read each of these as a 16-bit number, you get 15 bits which would be 5 bits per color channel, which would be a color. And now I'm wondering if this, well, I mean, there's quite a lot of it. It seems like more than 256, but it's so uniform and it matches so well. It's got to be something. And I've got a hunch this pattern looks palettes-y. There's just something about it which just kind of, yeah. Maybe there's multiple palettes. Maybe there's multiple palettes in this big chunk of information here. Here is the quick model I made for the proposed 15-bit color. Again, the components could be arranged around the other way. This is just a guess. But I'm also taking advantage of Mr. Crowbar's built-in color class, and really that just kind of gives you some nice abilities to say like print out the color and the ability to use it with palette objects, because palettes, all the palette functions are looking for these R8, G8, B8 properties. So the plan is I've got myself a test object here which just contains 256 of these colors. Let's try loading in this header at where the colors apparently start. Well, we've got information, and let's try printing it. So bx colors x print. Look at that. Look at that. This is so very definitely palettes-y. No, that's no mistake. That's got to be at least what we're looking for. So maybe the rest of the file is in fact just like different palettes for the same file. I'm not sure how, I mean, that makes perfect sense that you'd be able to do that in 16-bit. No idea how you do it in 8-bit. I guess some very careful management, but yeah, okay, there's like obviously a header at the top, which is a bit naff, but the rest of it, no mistake. This is as palettes-y as it gets. So we'll try. So let's try fixing the alignment and then see if we can get one of the other palettes. Or indeed, let's just try loading another palette now. Let's see what results we get. Yeah, similar. Huh, this one actually looks more similar to that, to the example that we kind of ripped from the EXE. Like, I remember that those shades of green. Yeah, so we've got that kind of earthy clay color, shades of green, dark gray, teal, white. Yeah, I think we found our location for the palette. At least for the title screen, because that all seems to match up. So we could probably use this to figure out where we are going off by. So yeah, right. So this very first color here in the palette is obviously a transparent one. So I assume it would be that, which then means we're off by a factor of 8 bytes. Yeah, okay. So if we give it 8 bytes for the header, this could actually be like a little subheader or something. But yeah, it looks like if we move this up by 8 bytes, then we should get the entire palette. Yep, that's it. I think we've got all of the colors, which is pretty cool. So that should mean, actually, now that we've got the colors, we should be able to go into our title. It was frames, yeah, frame 0. Again, do another hacky palette swap. There are cleaner ways of doing this. The clean way of doing it would be to use a ref, but no point going back and editing it now. So let's try that, change that for our colors. And then if we try and print this with small enough to fit on the screen, look at that! There it is. There is our logo in glorious 256 colors. In fact, we can actually make the logo full-sized if I just decrease if I zoom out a little bit on the terminal so it all fits. There's the logo. There is our desecrated logo. Again, just can't get over how beautiful this lovely hand dithering aesthetic is. They've put so much effort into such a small space with, in this case, an absolutely massive color palette, but you can tell they haven't really used that much. They've only really used kind of like this brown shade here, the acidic green, and maybe the stone color. Slightly higher than 16 colors, but still remarkable what they've managed to pull off. Now remember how a lot of those images were in that packed 4-bit format? So for complicated cases like packing or compressed data, Mr. Crowbar has transforms. A transform is just some raw Python code that converts one set of bytes to another set of bytes, and you can slot them in pretty easily into most fields as a sort of pre-processing step. Here I've written a transform class that is pretty basic. The import step splits every single byte into 2 4-bit numbers, and the export step does the reverse. One little bodge I had to put in was that the packing and unpacking steps, they should only happen if the image had that 4-bit flag switched on. So if the enable flag is set to false, then the transform just short circuits it and returns the buffer without changing it. Then all we need to do is add this transform to the field which contains the data. So this raw data here now has the transformation. We also wire up that 4-bit flag to the enable parameter, and we should be ready to go. You know what? I think I'll have a look at that snappy fish that I saw earlier. Yep, the fish is there. And there he is. Such a happy lad. And wonder what's going on in the other frames. Oh, oh, what a treasure he is. I love everything about this art style, I really do. For those playing along at home, the models from today's work file have been added to Mr. Crowbar under lib.games.lomax, and there's still plenty more to discover. Get yourself a copy and have a poke around. To play us out, let's just print all of the animation from main.world. I've made a little function for it here in the work file. And if I run it... And there you have it. We've successfully reversed the graphics in Adventures of Lomax. Now obviously, not all game formats are going to be this straightforward. We were lucky this time that it could be done entirely with guesswork and editing, or black box analysis to give it its formal name. Usually reversing is a mixture of techniques like this and also probing the code of the program in order to get more answers. But hopefully this should give you some ideas for how to use black box analysis in your own projects. Thanks so much for watching. I think this will become a regular thing, so if you have any questions or suggestions for other cool things to take apart, you can get in touch with me on Twitter. In the meantime, best of luck with all your research.